All right, everyone, take a seat. Take a seat. All right, so welcome to Wednesday. This is lecture 24. We are going to be interpreting confidence intervals, which is a little bit of a lie because we're going to review the bootstrap because I think it's confusing and no one had questions. So that's a concerning signal for me. So we're going to go back and talk a little bit more about the bootstrap. Then we're going to go through the confidence interval calculation. We'll think about interpreting them. We'll go through some discussion questions. And then if there's time, I'll actually try to jump into Friday's lecture and start to talk about center and spread. That is the plan for today. I doubt there will be time, so the ending set of slides will probably move to Friday. All right, so announcements. First, what announcements do we have? Homework 8 will be released tomorrow and due next Wednesday. That is the correct date. Yep. So homework 8 coming out tomorrow. Lab 7 is due this Friday at 11 p.m. And the thing you're all wondering about, midterm scores and score reports will be released today. Noah, do we know when they'll be released? Sometime today. I don't know what they look like. Do you know how they'll be released? By Ed? Ed post. Okay, so check Ed. There'll be a post. I should know all these things, but I do not. All right, any questions about announcements? This is the easy part. Cool, okay. All right, so estimation, that's what we've been thinking about. All right, and so this, again, is a big part of data science, a big part of statistics, is being able to make decisions or make, not decisions, estimate values of things that, we don't know. All right, and so all this starts with this idea of a parameter. The parameter is a fixed quantity. It is the truth. It is out there. We don't know it typically. So it's a fixed quantity in the population. If we have a census, if we have all the data, we can compute the parameter. We can compute it on our data. It is a fixed quantity that we can know. But in practice, that won't be the case. So how do we figure out an unknown parameter? We don't have an access to the population. We don't have a full census. So you don't have a census. You take a random sample from the population. You use a statistic. This is a function, essentially, from our data to a number or set of numbers. They're going to help us estimate the value of the parameter. Typically, especially in this class, the statistic would be the function that would compute the parameter if we had the census. We don't. We have a sample. So we'll take that function and apply it to our sample. We'll get a thing that is the value of what the parameter might look like on our sample, but it's called a statistic. And then we're going to see how that compares to the parameter for our population. Now, again, in practice, we don't have access to the population, so there's no way to know how it compares directly because we can't compute it. So we're going to use simulation methods to give us confidence intervals that capture not just the point, but kind of a range of values that we believe the point might be in, that the parameter might be in. That's the setup. So one sample, we got to make one estimate, and we want to go from one estimate to something a little more capturing our uncertainty. And that is because we're taking random samples. So again, the source of randomness in all of this is going to, we are using Bootstrap and simulation, but we're going to run that so long that that is not actually our dominant source of randomness. That's not the thing we're worrying about. The thing we're worrying about is we took a sample at random from the population. If we were to do that over and over again, we'd get different statistics, different estimates for our parameter. So we want to know the variability in our estimate. This is where the Bootstrap came in. So I talked about Bootstrap. It's a English colloquial jargon that's saying, it comes from the saying that you could pick oneself up by the straps on their boots. So it's an impossible task. We're using what we have to do something we shouldn't be able to do. We're using our sample to try to reason about the population. That was a setup. So as I said last time, I'm trying not to change this course radically. So I've used up until now mostly slides from this class. I decided to make a few new slides to try to illustrate the Bootstrap. Maybe that'll help a little bit. So here's our story. So we have a population. Here I've picked the population of the world at some point in time, past. The first step in our data science, our statistical journey, if we want to ask a question about the population, it is too expensive to ask everyone in the world something. Not only is it too expensive, it's going to be really hard. The US tries to do this with the census, and it is really hard. And there's a significant risk that they miss people when computing the census. They do the best they can. Not that good. Actually, some statisticians might argue that a sample better constructed could be more representative than trying to force the census on the population. It's really hard to build a proper census. So we take a sample. Now, when we take a sample, good practice is you ask, a question to a person, you write it down. You don't ask that same person that same question again, because you're over counting that person. So when we take a sample from our population, we typically do this without replacement, right? So you go and you ask someone, you pay them maybe to complete something. Actually, just as a thought exercise, how would you get a random sample of students at Berkeley? How would you do that? Let's actually pause here. Talk to the person next to you. How would you get a random sample, like a good, simple random sample, equally representing everyone at Berkeley? How would you do it? Talk. 1 minute. Warm up. All right, I lied. Less than a minute. I'm going to pick someone at random, simple random sample from my audience for a sample. We're going to just, who am I pointing at? I don't know. Someone on this line. How would I get a simple random sample? All right, that's my first problem. Oh, someone's going to answer. Thank you. Very good. That's great. That's how I would really do it if I had to do it. I'd say, look, I'm going to get all the student IDs at Berkeley. Is that representative of Berkeley? I think so. Okay. The student IDs, you can't be a student without student IDs. So I get student IDs. I put them in my Python. I do sample. I sample 50 student IDs. Now I got to go find those 50 students. I must find those 50 students. All right. So what happens next? I want to know what is their favorite color? That's my goal. What's the proportion of favorite colors? That's maybe the statistic I want to compute. So I have the 50 students. I go find them. I can knock on their door. I send them an email. I send them an email. They go what? Archive. No response. Right. So I've already started to hurt my sample. I need a simple random sample. I chose 50. If people can just choose to not respond to me, that doesn't work. So it's a lot of work. If I commit to that 50, I really need to make sure that 50 fill my survey. One way to do that is to pay them. Say, hey, $100, fill in my survey. And there's a good chance I'll get a good response rate. Of course, some people are like, yeah, $100 is nothing to me. So I have a sample bias now, right? The people who chose not to do the survey, I don't know, their favorite color is gold, right? So there's a challenge in getting a sample. So we work really hard to make these samples. Now we've got the sample, we've computed colors, and we're like, well, what is the fraction of students who really do like blue? Like I got a sample, I have an estimate. How do I reason about how it would have been if I ran that sampling process again? That is where the next step comes in. This is our original sample. Normally, you would stop here and compute the proportion. And you say, I have fractions of people liking each color. And I'd say, that is what I believe the population fractions are. That is my statistic. And the population fractions are my parameter. But I want to do better. This is where the bootstrap comes in. So I take that sample and I go, you know what? That was a big enough sample. I think it kind of, I hope it looks like my population. Let's pretend for a moment it is my population. Now I have all the data there, so I can ask those people questions. I can virtually ask them many, many times and see how it would perform, right? So I go back to that sample. This kind of looks like the population. Now I'm going to sample with replacement the same size, right? Conveniently, these people are color. So I can use the color as the definition of their preference. Okay, so these are the people, this is their preference in color. This is the green person. I sampled with replacement, so that person showed up twice in my sample. That's okay. That's what we expect to have happen. The important thing is that there are 4 people here. and there are 4 people here. So sample size has to be the same. Why does it have to be the same? Make it smaller. Make it larger. Oh, so yeah. Yeah, so I'm trying to simulate the process that I did in the first place, right? So I asked 50 people. If I'm going to simulate that, I should ask 50 people again, right? If I asked 2 people, then a lot of times my samples would have, no preference for a specific color. And I go, wow, there's a lot of variability in this sampling procedure that I just did. And that variability is because in my Bootstrap, I made my samples not the same size as my sample from the original sample. Okay, we'll do this many times. I don't think we've said this yet in this class, but we're actually doing a Monte Carlo simulation of this process. So we're doing many, many samples. And the idea is if we do this subsampling routine, which we can do on a computer, and it basically just costs time. If I do that long enough, it's going to converge to some distribution of the behavior of the thing that I'm trying to compute. Like I keep sampling and the statistic is just not changing anymore, right? The distribution of my statistic isn't changing. So I have all these samples, and notice again, with replacement, so there are duplicates. Duplicates are expected. Then for each of those samples, I take my statistic, my function, the median, the mean, the fraction of people that like blue, and I compute that on each of my samples. Got it? So I end up with numbers, or maybe a collection of numbers. So I'm computing a fraction of people that like each color. Then I can actually treat all of these samples as data, and I can compute empirical distributions of these statistics from all of these samples. Right? And then using the empirical distribution, I can ask questions about the sampling process. So what is the, if I were to pick a reasonable range of values, what would cover, 95% of the medians or the 95% of the statistics that I computed? And that's how we build our confidence intervals. So I think in last lecture we used the median. So we're looking at the statistic as the median. We computed the distribution of medians of incomes. And then we said, what would be a 95% confidence interval? So we take our distribution of medians. We want to cover 95% of the data, the center 95%. So we're going to take 1 minus 95, divide it in half, and that is our percentiles on each side. Right? This is the region here and region here. So 2.5 plus 2.5 equals 5, right? And I want everything between here and here. So what fraction of my data is here? 95%. And so what are the cutoffs here and here that would contain this 95% of my data? So in a moment, we're going to go implement this again, the code to compute this confidence interval. But before I do that, are there questions up to this point? Yes. If we were to use a p-value cutoff of 5%, would those 2.5% on either ends be statistically significant? You're getting ahead, but yes, we can use these confidence intervals to do hypothesis tests as well. Other questions? I'm going to do a silly poll. Raise your hand if this is making sense. People are feeling more comfortable. That's good. I'm a little surprised, but we're kind of explaining. So Bootstrap and words. You know what? I'm going to skip this and we're going to just go to some code. All right, so here's my notebook. Let me make it bigger for everyone. Okay. All right. So in the last lecture, we loaded in the San Francisco public employees salary database. And this was a census. Why is it a census? Well, sometimes when you're trying to study all the things in your database, if that is your population, in this case, public employees, and I happen to have the payroll records for all the public employees, I get lucky and I can get a census very easily. If I was, asking what are the grades of students in my class, well, if we had finished calculating them, I could answer that question. But once we finish calculating the grades of the students in the class, then I have the data, I have a census. None of anything I'm talking about today is relevant then. I just calculate whatever I want on the students in my class. So what we did Monday makes no sense because we had access to all the data, but we did it anyways because we wanted to illustrate how these techniques work if we did actually know the population value. So you can sort of check them. But you wouldn't do this in practice. Let's proceed to do this. Okay. So we had this histogram. This was the true histogram of salaries. Quick visualization review. Which way is it skewed? Skewed left. Skewed right. Skewed right. Very good. Yeah. So the tails go off to the right here. That's pretty common with incomes. Usually it's more peaked here. So we have salaries and San Francisco are actually pretty good. They're not just skewed, not piled up on the left here. Right. Off course. Okay. So we wanted to define a statistic. So we made a statistic last time using percentiles, a concept we introduced last time. I want to compute the median. How do I do that? The median, T is going to be a sample. Let's call it a sample. How do I compute the median? Someone help me. Percentile. I need a number. Yell out. 50. Very good. And then what? Sample. Done? So I've done this mistake a couple of times when working through this exercise. No, not done, because that's a table. I want a column, right? Which column do I want? Total compensation. Cool. Did I spell that correctly? I think so. Okay. So I've implemented a percentile. What was the definition of a percentile? I get this wrong every time. So 50% means what? I sort my data and I find the smallest value in my data. So percentiles for this class are always a value in my data set. Such that what? Yeah. Yeah. 50% of the data is at least as large as the value I chose. Is that right? Is that right? At least as large. Sounds right. Yeah. That value has to be at least as large as 50% of the data. Yeah. Correct. Yeah. Were there confusions about percentiles? We went fast on it. I always find this definition hard to parse. Pictorially, it's very easy. I sort my data and I find where 50%. And if that lands on a data point, that's my point. If not, I go a little bit to the right to the next data point. Are there questions? Yeah. What did we actually say in lecture? I forget. The pth percentile is the first value on the sorted list that is at least as large as p% of the elements. Yes, so what you said. So at least as large. All right. The reason why this is weirdly pedantic is these things have to make sense when all your data is like stacked on one point, when you have a bunch of duplicate values and so on. And it has to work for the 0th percentile and the 100th percentile. I will say that if you go and use percentile tools in NumPy, for example, it doesn't use this definition. It's a slightly different one, and it does interpolation. But this one is good for this class because it picks out a point in my data set. Always a point in my data. All right, other questions about percentiles? Let's keep going. Compute median. I did this right. Okay, cool. So that is the population median. If this were our goal, we have estimated the parameter, we are done. We can close shop and go home. But the point of this exercise is that what if we didn't have access to all that data? What would happen? How would we do this if we worked with just a sample? Good news. I happen to have constructed a sample. Okay, don't click on that. So I built a sample here. I went out and I asked a bunch of employees. I asked 400 employees what their salaries were. That is a sample. That is more reflective of real life. My initial sample, that's that first sample for my population. And then in last lecture, we introduced the Bootstrap and we implemented the code. I want to walk through this once more, though I think everyone's getting it now. So a bootstrapper here, this function, takes in a sample. That's my original sample. A statistic, that's a function. Is it weird that I'm passing a function in? Who's comfortable with that? That's okay. Who's like, that's a little weird? A little weird. Okay. Yeah, so we can do this. Let's just very briefly review what happened here. Oh, no. Okay. Up here, I wrote this function. It's a function. Functions can be things too. So that is a function. I could even say q equals that. Now q is also a function, right? So functions can be values, can pass functions around. Very useful because now I can have a piece of code that I wrote that takes in a function and uses that function inside the code. All right. So let's use it. So I have my function and I have a number of repetitions. You should make that number as big as you can. So here I'm going to take my bootstrap stats. This is going to be an empty array. And then number of repetitions times, I'm going to take my sample and sample it with replacement. And sample.sample returns exactly the same number of elements with replacement. That's those separate samples in the far right of my earlier illustration. That's my bootstrap sample. I guess we go to the pictures here. Yep, so these are my bootstrap samples. These are the little people here. Now, I want to take my statistic. That is this function here, stat. I'm going to apply it to my sample. So statistic, there's my function. I'm treating it like a function, applying it to some data. And I'm going to get back, in this case, a number. And I'm going to add that number to my collection of statistics and return those collections of statistics. That is the bootstrap in code. Cool. Run it. Ooh, that's bold of me. So I'm going to run this 10,000 times and ask questions. Anyone have questions? Take a little bit of time here. Reading the media. Yeah. It's okay that a variable has the same name as a method. Okay, yeah, that's confusing. All right. We're not teaching object-oriented programming, but in computer science, there's this concept that I can have a thing, table, a sample, that has methods on it, sample. Yeah, it can have the same name. I think is where yeah, this works. Yeah, you can always do that. If you take the 61 series, then you can start to learn how to build these objects yourselves. But in this case, we have an object table that we call the sample method on. Sample.sample. Good beat, yeah. Why is it important to get the median value? Right, so the statistic I've chosen, sorry, the parameter I've chosen in this exercise is what is the median income, total compensation for employees in the city of San Francisco. That's my goal. So my statistic is the median, and I'm applying that statistic to each of my data entries. Quick aside, which is getting into next lecture. Why didn't I choose the average? You already know about the average. Yeah. Good. We're going to talk more about this at the end of this lecture, or at the beginning of next lecture. The average is kind of sensitive to people who make too much money, right? So if you have someone who makes a lot of money and you compute the average, it's like, wow, people like, it's skewed to the right. I'm going to pick up that skew. The median, the people who make way too much money over there, it doesn't matter because the middle is still the middle, right? So you take the wealthiest person, you just keep making them wealthier. The median doesn't care. The average does. So when talking about things that are really skewed, we typically use the median. Think about the center. Okay, so we did that. A little bit of time. And let's see what we got. All right, so there's my my median. Sorry, this is the truth. You don't get to know this normally. We happen to know it because we cheated. And then this is the distribution of medians that my sampling procedure created. The distribution of medians. So on each of the sample, I get a different median. This is what that distribution looks like. Not the distribution of income. Cool. All right, so now we want to build a confidence interval. I'm going to make a function this time to build a confidence interval, and you're going to tell me how to implement it. And maybe I won't even look at my iPad. I might look at it. Okay, here we go. So I'm going to say this function takes in my bootstrap samples, so all 10,000 medians that were computed, and a confidence level, say 95. All right, so what is the size of the tails? Let me go back to my picture over here. I need help calculating this. Oop. This is 2.5. How do I get that number, 2.5 from 95? What do I need to do? So I have 95 is my confidence level. It's not my tail size. The tail is whatever is left over, so what's not in the center. So 100 minus that. That's what's in both tails, but I want the value for each tail. So what do? Take this number, and someone said it, divided by 2. Nailed it. Did I do that right? Yes, I did. Confidence, Joey. Okay. So now, how do I compute the lower cutoff for my confidence interval? Someone yell something out. Median. No, something. Percentile. Okay. And then I want what? Tail size. So I want the lower tail. And then I want what? My BS, that's bootstrap. BS samples. Good? That was easy. Okay. How about the upper? It's going to take some thinking. Percentile. Tail size again. BS samples. Nailed it. No? Why is it wrong? Well, they're going to be the same, so that's not a good start. And with the other tail, go back to our picture. So I want this. So here, this is 100. I want to go back 2.5, right? Right? How do I do that? Any number here. What number? Someone yell it. 100 minus tail size, right? Questions? Corrections? Did I get it right? All right, so that is, let's assume that's right. That's my lower. That's my upper. Those are going to be numbers in my bootstrap samples. And I'm going to return a list of lower and upper. Cool? My function. I've documented my function here to explain what it does. Little side note, if I document it, when I hit Shift Tab, it tells me what I wrote there so I can remember my arguments. Whoop. Yeah. No, go away. Okay, this is killing me. Where to click on that. Okay, so now I'm going to run my confidence interval function on my bootstrap medians and get my 95% confidence interval. Good. Let me show you a cool trick. Did you know you can do this? Left, right, equals CI. What's that going to do? Left. So lets me take that confidence interval and pull out the pieces. It's useful when we're playing with these little lists or little arrays. Cool trick. They need to know they don't do this. Yeah, I don't think we covered this in lab. So let me hide that. Doing me really annoying. Okay, cool. So confidence intervals. So let's look at our confidence interval. That is our confidence interval, the yellow region here. And that contains the truth. So we got lucky. Good. So we did this last time. So return to our slides for the interesting stuff now. So we did this in words. Okay. Confidence intervals. We walked through the estimating of the parameter based on a random sample. 95% confidence level could be a number between 0 and 100. Higher level means the interval is going to be wider because we're going to grab more of that bootstrap sample. Smaller, less confidence, but more precise on our answer. Or smaller range of answers. So a good interval is one that contains a parameter. Do we know if an interval is good? Typically, no. We don't get to know that in advance. And the confidence is the confidence in the process that creates the interval. So it generates a good interval with about 95% of the time. I'm going to restate that in a few moments because that's very important. Okay. Let me walk through just a quick picture here. I've taken many different runs of that whole procedure. So this is, actually I built this out. So what is the meaning of a 95% confidence interval, which is the whole point of today's lecture? The green line is the parameter value that, again, you don't get to know in the real world. We get to know it here to make a pretty picture. All right. It is fixed and it is unknown. So we view the parameter as the truth. It is out there. It is not random. We just don't know it. Okay. For the purposes of demo, we actually had access to it, but we're cheating. All right. The yellow lines here, each one of these little yellow lines is a different 95% confidence interval based on a fresh sample from the population. So the source of randomness is that initial, I paid 50 people and asked them questions. Okay. So that is the randomness that we're talking about when we have the random process here. Not my random simulation, that's the bootstrap, because I've run that so long that it's converged. It's not the source of randomness. Okay. So if there are 100 intervals, we'd expect roughly 95 of them to contain the true value. Questions? Use methods appropriately. Let's go back to the slides. I think there's something kind of fun here that we can walk through. All right. So I'm about to do this thing that I like to do. I'm going to simulate my simulation. So remember that all those yellow lines? Let's do that again. This time what I'm going to do is I'm going to simulate 20 times. I'm going to go back to the population, get a new sample, then run my whole bootstrap procedure, and then get a confidence interval. I'm going to do that again 20 times. And I'm going to do for each of the 20 times, I'm going to take a sample size of just 2, then 4, then 8, and then 16. And then we're going to think about what happens to those intervals. What will they look like? And actually, before we do that, take 30 seconds. Think through what will happen to those intervals. Will the 2 interval be nonsense? Will it be really wide? Will it be really small? The 4, 8, 16, what's going to happen? Take 30 seconds. Talk to people. In fact, while you do that, I'll run this simulation. Okay, so what's going to happen? Hold that thought in your head because let's actually see what happens and see if it reflects what you expected. I'm not going to walk through this code other than to say the key point here is each of these 20 times I'm taking a fresh sample from the population because the source of randomness is that fresh sample, and then we run this bootstrap procedure on that sample to get a confidence interval. Walk through the code, it's good exercise. I'm going to use some plotting code we're explicitly not teaching you in this class, but I think it makes prettier plots. So here's what the visualization of this looks like. Go. All right. So what do we have here? So the purple ones are sample size 16. Okay. The black line here is the truth that is out there that we don't get to know. To that in a moment. But we get pretty good results, right? These intervals seem to generally capture the truth. I've made the empty circles ones where it missed it. So we missed here, right? We expect a few times we'd miss out of 20. Kind of expect one time we hit it twice. We missed it twice. It's unfortunate. Okay. As we went to a smaller sample size 8, what happens? Our intervals become a little wider. They're still maybe trustworthy, but they start to have more misses, right? As we go to sample size 4, they get really wide. We got lucky and have a fair number of fair number of hits. So again, they're very wide intervals. So we're not saying very much. So the income could be any one of plus or minus. What's the actual value here? plus 168K minus 99K. So that's a pretty broad spread, not very helpful. Trying to say what's the median income, right? And then it's size 2. These are just all over the place, right? They're too small. Okay, so takeaways. If you're going to do this whole procedure, make sure that your sample is reasonably large. And we'll talk in a moment about what you should look for you should actually plot the distribution of the statistic and make sure that it's roughly symmetric and kind of concentrated around a center point, what we would call as bell-shaped, and we'll talk more about that. You want to have enough data that initial sample is reflective of the population, because that was our assumption in the initial setup. And as you add more data, these intervals will get smaller and smaller. Questions? Full picture. Okay. I think we can return to slides here. All right, so using the methods appropriately, let's review what I just said. When not to use our bootstrap method. Here. Okay, if you're trying to estimate any parameter that is greatly affected by rare elements of the population. That's very confusing. What does that mean? All right, so you should not use the bootstrap. In fact, the whole sampling process is going to be pretty flawed. If you're saying, what is the wealthiest person in the city of San Francisco? That's really hard to sample, right? Because you're not going to answer that correctly unless your random sample hits that one person that happens to be the wealthiest person, right? So these extreme events. How about the second wealthiest person? Third, fourth. Yeah, so these far extreme events are hard. Median's a little funny because there's one person, maybe, if everyone has a distinct income, there's one person who's the actual median, right? We'd expect that the median, the people around the median have fairly similar income. So if you miss that one person that's truly the median, you get the person right next and they make just a little more or just a little less, right? So the median is pretty well behaved. Things like the mean, generally pretty well behaved unless there's that one person who makes $1 trillion, and then your sample is going to be in trouble, right? Because if you miss that $1 trillion person, your mean is, reasonable. And if you get that $1 trillion person, your mean's all of a sudden enormous, right? So we need to pick things that aren't greatly affected by extremes in our population. We also want the thing that we're trying to reason about to be reasonably well behaved, so that sampling in the first place will actually make sense. Kind of vague questions about that? Yeah. Great question. Why the median is stable, but you could take the mean and exclude outliers. There's a term for it, Winsorizing. We can use techniques to try to exclude outliers. People do that. In general, when you're looking at these what are called heavy tail distributions, where there's these long tails, which is actually common in a lot of problems, the median is the standard kind of robust go-to statistic that people would use when trying to think about the center. Yeah. Partly here because you'd have to exclude a lot of people. Like there are, a fair number of people who are making 700K, 500K in the city of San Francisco. They're not outliers. They're like, that is reasonable pay for them, but we don't want the whole distribution to be sensitive to them. And so directly throwing away them as kind of anomalous points in our data isn't typically the approach. Okay, so we don't want very high or low percentiles, min and maxes are things not to do. If the probability distribution of your statistic is not roughly bell-shaped, the shape of the empirical distribution will be a clue. So, right, break these into two bullets. All right, so the next thing to look out for, and I said this earlier, is that once you've computed your bootstrap, it is customary, not just customary, a great idea to make this histogram. So is that histogram roughly the shape of a bell? The bell that you ring like this, should have an icon of a bell. So this is my bell here. Is that roughly bell-shaped? Who says yes? Who says no? I say I'm concerned, actually. There's a point out here. There seems to be some variability, some tails in this distribution that I should be a little worried about. I would still say this is roughly bell-shaped and probably move on. I might want to buy a bigger sample just to see if I can make that a little more bell-shaped, but yeah, that's what we're looking for. Something that is more or less like this. Ideally, there isn't a bump over here. And our histogram tool suggests there's probably a bump over here that's basically 0. So it's still a little bit skewed. There's like one weird outlier. But this is great. This is what we want to see. And if I'd used the mean instead of the median, I would probably get something that's more just this, my bell. So if that's the case, the bootstrap is going to do superbly well. Okay, bell shape. And if the original sample is very small, so 4, 16, maybe even 32, those might be pretty small samples to try to run a bootstrap. Do people do it? Yeah, so sometimes that's the best you've got, and you're going to do bootstrap estimation because that's the best that you can do. Okay. I'm going to do a quick aside. You do not need to know this, but if you were trying to use a bootstrap in real life, there are ways to improve this confidence interval. The one we've taught in this class is the simplest. It's actually pretty good. It's the one that was originally proposed, but statisticians have been studying this for a while and have ways to improve that estimate. So you could look at that if you were really trying to apply these techniques in these kind of weird situations. So not all hope is lost. Okay. Questions? Cool. Again, I assume people know what's going on. I have a demo that I wanted to show you for the extremes. We did simulation. Okay. Let me just quickly run through one more example of this. Here, I'm going to use the births data that was used in previous lectures. This is a sample of women and their babies who just given birth, I think, in the Bay Area. And so here's a good use of where we don't actually have the population. And so I could ask, like, what is the average age of moms when they give birth? And so there is a truth about that in the population. And maybe my whole population is the US, or maybe it's the Bay Area. Let's say it's the US. There's a flaw in that, but so my whole population is US. I have the sample of the Bay Area. My statistic here is going to be average. Why not median? Because I don't expect it to be a huge skew, right? This is something that hopefully is a little bit more, bell-shaped in the first place. Yeah, and we can look at that. A little bit skewed, but no extreme points here. Okay. Right, so I want to estimate statistic. I could construct a percentile. That's the median. So the median age of a mom when her child is born is 26. I could also construct an interval. Is that a confidence interval? What is that? It's 95%, or it's 2.5 and 97.5. What is that? That is not a confidence interval. That's just an interval. I took 95% of the ages and I took the lower and upper end of it. That is not a confidence interval. You will do this when making like box charts. You pick the lower 25 and the upper 75. Those are quantiles, but these are not confidence intervals. Okay, so same game. I define my statistic function. Takes a sample. I'm going to compute the average and the maternal age. I can compute that on my sample, 27.22. I'm going to bootstrap my means. How do I do it? Bootstrapper. Okay. And then what do I want? I want the sample, which is what? What do I put here? Births dot column, maternal age, my sample, and then statistic is going to be called average maternal age. And how many do I want? How many do I want? Let me just actually make sure I don't ruin my exercise here, because we're low on time. Wow, I chose 3,000. How bold of me. Okay, so 3,000. Does that look right? Did I do that? So I did something wrong here. Not entirely wrong. I didn't need to project this out. I just need the births. Because my bootstrapper, the way it's going to work is going to take samples, and then for each of the samples, it's going to apply the statistic function. That's this guy up here. And that does the collecting out the column. Okay, so I have my bootstrap means. If I did this right, how do I get my confidence interval? Just reusing my code from before. I have compute CI, my bootstrap means, and I have my confidence level. I want a 95% confidence interval, so I say 95. What did I do wrong? Did I spell this wrong? No. You're right. That's not valid code. Okay, there we go. Right, so that's building my sample, just like we did before. It's getting redundant now, so you're all probably like, yeah, I'm sick of this. Will we wait for 3000 to compute? So we'll make one picture, and this is good. We're interpreting complex intervals. Okay, so that is my interval, 26.9 to 27. That's a pretty small interval. What does that look like? That's my distribution. Now that is a bell-shaped distribution. I trust this interval. Good interval. Okay. And there is my distribution of maternal ages. There's my confidence interval. Little guy, right? Not big because it becomes on my estimate of the mean, right? Not on the ages themselves. I'm not trying to describe the range of ages. I'm trying to describe the mean and my confidence, my range of means that I think, are likely to be the parameter of the population. Okay. Turn to slides. All right, so some questions. All right, so by our calculation, approximately 95% confidence interval, the average age of mothers in the population is 26.9 to 27.6 years. True or false? All right, someone tell me the answer. I'm actually not sure. Someone. About 95% of the mothers in the population were between 26.9 years. I guess I have to ask this question. Yeah, is this the true or false statement? Is this statement true or false? About 95% of the mothers in the population were between 26.9 and 27.6 years old. False. Why is it false? Because this confidence interval is about the mean, not about the population. We calculated that earlier. There's a much wider range for the age of mothers. So false. We're estimating the average. The confidence interval is a statement about the average age in our sample. Okay, we did that already. Is this what the CI means? An approximate 95% confidence interval for the average age of the mothers in the population is 29.6 to 27.6 years. Sorry, 26.9 to 27.6. True or false? There is a 95% probability that the average age of mothers in the population is in the range of 26.9 and 27.6. This one's tricky. Quickly discuss. You have 30 seconds, go. And I'm going to pick someone at random. At random. So make sure you know the answer. All right, everyone knows the answer because not enough people are talking. Are you sure? All right, someone on this line, give me the answer. True or false? You can pick one. True. All right, someone on this line, true or false? True. Okay. False. Yeah, I thought that too, actually, when I was doing this, true or false. All right, so here's the thing you gotta remember. I did this sample. I have my confidence interval. That's a number. I know it. There's a parameter. I don't know it, but it's not random. Okay. So the confidence interval, the way we interpret it is a statement about the frequency. If we were to do this repeated sampling of confidence intervals, the fraction of intervals it would contain the parameter. It's not a statement about the particular confidence interval we have. It's a statement about the process that generated that. That's a little confusing. Questions about that? So I'm going to put this up once more. So an L% confidence interval means if we repeatedly follow the same process of randomly sampling from the population a sample of the same size and apply the same CI calculations, then we'd expect L% of the interval will contain the population parameter. Fine print, assuming that the samples are large enough and that the statistics are well behaved, and we ran many bootstrap samples. Okay. So the randomness in this process is that initial random sampling. Once we've done that, we've got a confidence interval. It's not a statement of a probability now. Okay. We're done. See you guys on Friday.